Okay, I'm back and we're going to continue our work on differentiation and its applications. One of the first things I want to do is to correct one of the problems that I had in the previous worksheet. As you can see here in red, I'm saying this is a correction from the previous video. Problem number 3 on the worksheet should have been find the equation of the tangent and normal to the curve y is equal to x squared minus 1 times x plus 3 at each point where the curve meets the x-axis. I think what I had there was x squared plus 1, and that would have only had 1 point where the curve meets the x-axis. This one has 3 points where the curve meets the x-axis. So effectively, this is the one in which you would have had 6 different, 3 tangents and 3 normals. All right, so please redo that problem. That's my mistake. Let's continue. The first heading here I'm looking at is finding the point or points on a curve where the gradient has a given value. You would notice before what we were doing, we were using the point, certainly the x-coordinate of the point, to find the gradient of a curve at a given point, at that given point. Here, I want to give you the gradient of the curve at a given point and ask you to tell me what the coordinates of the point are. So let's see the connection. I'm going to redo this first one, in which we're going to use the equation. I'm going to give you the x-coordinate of the point, and you're going to find the gradient. Here it is, number 1 right here. We've done this already, but this should be a good recap. Find the gradient of the curve y is equal to 3x cubed minus 12x plus 19 at the point where x is equal to 1. Well, obviously we know we have to find the gradient function first, dy dx. That's equal to 9x squared minus 12. This is my gradient function. My gradient function depends on x, so I simply plug the x value into that gradient function. When x is equal to 1, dy dx is equal to 9 times 1 squared minus 12. And I think that's 9 minus 12. That looks like minus 3. That number is the gradient of the curve at the point where x is equal to 1. It's also the gradient, as you remember, as you should remember, of the tangent at the same point. Good. So, given a point, or at least the x-coordinate of a point, we can find the gradient of a curve, or the gradient of a tangent to the curve at that point. Okay, let's come down here. We are now interested in the reverse process. That is, given the gradient of a curve at a point, can we find the coordinates of the point or points on the curve where the gradient has that specified value? Sometimes you end up in more than one point on a curve where the gradient has a certain value. Can we do that? Well, let's jump right in. The concept is as follows. What you would do, you would find the gradient function, dy dx, and then you will equate the gradient function to the specific value of gradient. That's the idea. Give me a minute here. All right. To accomplish this, you simply equate dy dx to the specific gradient. And then you solve for x and y. Let's see how that's done. Here's my first example. Find the coordinates of the point, excuse me. Find the coordinates of the point or points in the curve. Y is equal to x minus 4 times x plus 3, where the gradient is equal to a half. Okay. So let's first find the gradient function. Based on the only method of differentiation we know, we have to open up these brackets. So y is equal to x squared. Well, that should be plus 3x minus 4x. That's minus x, I think. Double check my algebra there. And minus 12. X squared minus 4 plus 3 is minus 1. Yes, and therefore dy dx, the gradient function, is equal to 2x minus 1. Yes, dy dx is equal to 2x minus 1. We want the point or points on this curve where the gradient is a half. So we will simply equate dy dx to a half. That means that 2x minus 1, which represents dy dx, is equal to a half, from which we can solve for x. What's the best way to do this? Throw the 1 over, you get 2x is equal to 1 plus a half. That's 3 halves. And therefore, x is equal to 3/4. So, at the point where the gradient is a half, the x-coordinate is 3/4. Let me double check that. 1 plus a half is 3 halves. 1 and a half or 3 halves. Divide that by 2, you get 3/4. Okay. And now that we know the x-coordinate of the point, we simply go back to the original equation to find the y-coordinate of that same point. The original equation was y is equal to, I'm going to use it in the expanded form, x squared minus x minus 12. Y is equal to x squared, 3/4 squared, that's 9/16, minus x, which is 3/4. 3/4 is 12/16, and then minus 12. I hate fractions. You know what? 9/16 minus 12/16 is minus 3/16. Minus 3/16, and then minus 12. This is embarrassing. 192 and 3, 195. Minus 195 over 16. I think. Y'all gonna double check my numbers. So, when the gradient is a half, when the gradient is a half, the point at which the gradient is a half has coordinates 3/4 minus 195 over 16. Voila. Not a bad concept, right? So let me reiterate. If you're looking for the point or points on a curve where the gradient has a specified value, you find the gradient function and you equate it to that specific value of gradient. And then you solve for x. That would be an equation in terms of x alone. You solve for x. You plug the x value back into the original equation to find the corresponding y coordinate of the point. That should be pretty decent concept there. Let's try the next example. This one says, here it is, find the coordinates of the point or points in the curve. And the equation of the curve is given where the gradient is -5. Okay, this shouldn't be a problem. Same concept, different equation. So let's first find the gradient function. Dy dx is equal to 3 by 1/3, that's 1, x squared minus 2x minus 5. X squared, yes, 3, x squared minus 2x minus 5. At the point or points where the gradient is -5, we equate dy dx to that -5. Equate dy dx to the specific value of gradient. And therefore, dy dx, which is x squared minus 2x minus 5, is equal to -5. If we tidy this up, throw the -5 over on the other side, we get x squared minus 2x is equal to 0. Factorize x into x minus 2 is equal to 0. X is equal to 0. X is equal to 2. So check it out. There are 2 points on this curve. I've just found the x coordinates of 2 different points on this curve where the gradient is -5. No problem. You simply take each x coordinate, plug it back into the original equation to find the corresponding y coordinate. So let me write back the y equation here. Y is equal to 1/3 x cubed minus x squared minus 5x plus 1. When x is 0, clearly by observation, everything with x will go to 0, so y would be equal to 1. So 0, 1 would be the coordinates of one of those points. The other one, when x is equal to 2, corresponding y coordinate would be 1/3 times 2 cubed minus 2 squared minus 5 times 2 plus 1. Y is equal to, this looks like 8/3 minus 4 minus 10. Minus 4 and minus 10 is minus 14 plus 1, minus 13. And that y coordinate looks like 8 minus 39 minus 31/3. So that point has coordinates 2 and minus 31/3. So if you were to summarize, there are 2 points on this curve where the gradient is -5, and those 2 points have coordinates 0, 1 and 2 and minus 31/3. Again, y'all, please check back my arithmetic with these numbers. Okay, that's the end of that one. There's one more example. Example number 3. Hey, come back up. Same instructions again. Find the coordinates of the point or points in the curve. Y equal root x plus 1 upon root x where the gradient is 0. Okay, we should be able to handle that with not too much fanfare. Clearly, this function is not in the form of a standard polynomial, so we will first put it in that form. So you're looking at y is equal to x to the power of a half plus, that will be 1 upon x to the half, which when you throw it up becomes x to the minus a half. Everybody can do that. You know your indices, right? Dy dx is equal to a half x to the minus a half minus a half x to the power minus 3 halves. Let's tidy this up a bit first. All the terms with the negative powers, we're going to throw them into the denominator. So dy dx is equal to 1 upon 2x to the half minus 1 upon 2x to the 3 halves. Looks like we have an LCM of 2x to the 3 halves there. That's x. Let's see, 2x to the half into 2x to the 3 halves. If you divide, you're left with x. X by 1 is x. Minus 2x to the 3 halves into 2x to the 3 halves is 1. 1 by 1 is 1. Okay, so this is my gradient function, dy dx. I need to find the coordinates of the point or points on this curve where the gradient is 0. Okay. So when the gradient is 0, when the gradient is 0, I put dy dx, the gradient function, equal to that specific value of gradient, which in this case is 0. So x minus 1 upon 2 times x to the 3 halves is equal to 0. If I transpose, cross multiply the 2x to the 3 halves by the 0, what do I have remaining? X minus 1 is 0. From which I can solve to get x is equal to 1. But now that I have the x coordinate of the point where the gradient is 0, I simply plug it back into the y equation. Remember, y was root x plus 1 upon root x. When x is 1, y would be equal to the root of 1 plus 1 upon the root of 1, which is 2. So when the gradient is 0, the point at which this gradient is 0 is or has coordinates 1, 2. So it's a pretty straightforward concept. All right, I'll just summarize it one more time for you. If you want the point or points in a curve where the gradient has a specified value, you find the gradient function dy dx and you equate that gradient function to the specific value of gradient. Solve for x and then plug back in and solve for y. That's it. That's the concept right there. Now, well, I'll leave that for the next worksheet, for the next tutorial. That's pretty much it for this one. I have a worksheet with several problems here. Let me see, 1, 2, 3, yeah, just 3 problems in this case. And knock yourself out. Let me see, find the point or points in the curve where the gradient has a specified value. Find the point or points in that curve where the tangent is parallel to this line. You gotta think your way through that one. All right, if a tangent is parallel to a given line, then obviously the tangent and the line both have the same gradient, which means the tangent and the line and the curve at a specific point all have the same gradient. Anyway, enough clues for that one. You figure out the rest. Find the coordinates of the point or points on this cubic equation where the gradient is 0. All right. There's a special name for points and curves where the gradient is 0, but I'll discuss that in the next tutorial. All right, that's it for this one. I'm out.